Okay, good morning. Up to now in the lecture, we discussed the language Haskell and gave a first practical introduction to Haskell so that you can really write programs in Haskell and have an idea what functional programming is about. So this was the practical part of the course. And in the remainder, we will look at the theoretical background behind functional programming. So in the second chapter that we will start now, we will look at the semantics of Haskell. So how can you define what language constructs really mean? How does that work? So we will look at how to do this for functional languages, and of course, as an example, we will do this for Haskell. And in the third chapter, we will look at how to implement Haskell. So after we defined what Haskell constructs actually mean, the question is how can you implement a functional language? And one way of doing this is using the lambda calculus. So this is the lambda calculus used for the implementation of Haskell.
Lass mal so Satzhausaufgaben, die können wir sicher gleich nach der Vorlesung bringen.
Die wollen Sie abgeben?
Ja.
Ja, okay. And then finally, one thing that the Haskell interpreter or the Haskell compiler has to do before executing a program is it has to do type checking. So we first have to check, are all programs well typed? And only in that case, they have a well-defined semantics and they are really executed. And how to do this type checking automatically, that will be the topic of the last chapter. So let's move on to chapter 2, so the semantics of functional programming. Semantics of functional programs. So up to now, we defined the syntax of Haskell. We had these grammar rules which told us what syntactically correct Haskell programs are. But we didn't discuss about what these programs really mean. Of course, intuitively, we made this clear, and by many examples, you have a pretty good idea what the different language constructs mean, but we didn't define this formally. So up to now, we had the syntax of Haskell, but semantics was only defined informally. We said, well, this operates like this, and this operates like that. So the semantics, we only handled this informally. And why is it a good idea to define the semantics in a formal, rigorous way? Well, the reason is that if someone wants to implement a compiler or interpreter, then he or she has to know what the language constructs really mean. I mean, if you just explain this informally, then people may understand this in a different way, and one person implements the compiler in this way, and another person implements a compiler in a different way, and then it depends on the compiler how your program executes, and that's, of course, not desirable. So the semantics should really be fixed in a clear, non-ambiguous way, and then no matter which compiler or which interpreter you use, the same things should happen. I mean, they might differ in efficiency, but they should not differ in the program behavior. So a formal definition of the semantics. Why is this needed? Well, it's needed if you want to implement a language. So it's needed for, well, an unambiguous implementation of compilers or interpreters. And in fact, only if you have properly defined what the language constructs mean, only then you can say that a program is correct or not. Because if it's not really clear what the program means, then yeah, how can you speak about correctness? So it's needed for the question whether a program is correct or not, so whether it satisfies its specification or not. So how can one define the semantics formally? Of course, you can do this not only for functional languages, but also for other kinds of programming languages. And there are two main ways of doing it. So, I mean, there are more than two, but the two most prominent possibilities to define the semantics are the following ones. So there are two main possibilities. to define the semantics of programming languages. One way is the so-called denotational semantics. And here the idea is that we simply define a function which maps every expression of the programming language to some mathematical value. So for example, an expression like 2 plus 1, which is a legal Haskell expression, would be mapped to a mathematical value, namely to the number 3. And a Haskell expression which defines the function square would be mapped also to a mathematical object, namely to the function that takes a number and squares it. So this is the idea to define a mapping from programs or from expressions and programs of the language, from expressions and programs to mathematical objects. And well, mathematical objects are things like numbers, lists, functions, things like this. And this, in fact, is what we will do in section 2. So we will define the semantics of Haskell in a denotational way. But there's another possibility, namely the semantics can also be defined in an operational way. And there the idea is that we simply define one interpreter and we say, well, what this interpreter does, that's correct. So this interpreter defines the meaning of the programming language. Every other interpreter or compiler that does the same thing as our interpreter is correct. I mean, it might be more efficient, but it should be doing the same things. That's the idea of an operational semantics. So here the idea is define an interpreter for the language, so which really executes programs, and the way that this interpreter behaves, that's the semantics of the programming language. So the idea is that every other interpreter or compiler that behaves in the same way is correct. So every other interpreter or compiler has to, well, deliver the same results. It might deliver them more quickly or more slowly, but it has to deliver the same results. And this is what we will do in section 3. So, I mean, in section 3, we discuss about the implementation of Haskell, and we give one example implementation of Haskell. And so you can see this as the operational semantics. Every other implementation should do the same, but it might be more efficient than our implementation, or less efficient. OK, so that's the plan. We will define now the denotational semantics of Haskell. And well, to do this, we will first introduce some mathematical background that we will need to do this. And we will do this in section 2.1. And in section 2.2, we will then really introduce the denotational semantics of Haskell. So let's start with the mathematical background that is needed to define the denotational semantics. And the main background are complete partial orders. What that is, we will see. These are also called CPOs. And fixed points. And we will see what that is and why we need this. So this is the mathematical background that is needed for defining the denotational semantics of Haskell in the next subsection. For the denotational semantics of Haskell. OK, so that's what we will have to do. And well, as I said, the idea of the denotational semantics is that every Haskell expression is mapped to some mathematical value. So, as I said, the Haskell expression 2 plus 1 will be mapped to the number 3, which is a mathematical object. But the problem is that in Haskell, there are also expressions that are undefined. If you think of a function that doesn't terminate, this function should also be mapped to some mathematical value. So there should be mathematical values that stand for undefinedness. And even worse, there might be functions that terminate sometimes and don't terminate for other inputs. Or there might be tuples where one component is a number, but the second component is something that doesn't terminate. So there are different degrees of definedness and undefinedness. And so we should first discuss about how do these objects, these mathematical objects, look like that we want to map program expressions to. And therefore, the first part is let's discuss about values that can describe definedness or undefinedness, or which are a bit defined but not completely defined. So values that are partially defined. So let's discuss about how these mathematical objects could look like that we want to use for our semantics. So the idea is we will define a function val for value, define a function or a mapping val, and this function val should map every expression, every Haskell expression, to some mathematical object. That maps every Haskell expression. I just write H, and H means Haskell. Every Haskell expression to a mathematical object. And so, for example, as I said, 2 plus 1, this is the Haskell expression, is mapped to a mathematical object, namely to the mathematical object 3. So this is a number. So in other words, this is a mathematical object. So this is rather clear what to do here. Similarly, if we have functions, we can also map functions that we define in Haskell to mathematical functions. So, for example, well, if we have this function definition square, where square is a function mapping integers to integers, and it is defined as expected. So square of x is x times x. So if we have this Haskell program, then square on its own is an expression. So square, what should we map square to? So square is a Haskell expression. Well, this should be mapped to a function, namely the function that takes a number and squares it. It's mapped to a function that takes a number and squares it, so it computes its square. And this, of course, is a mathematical object. I mean, functions are something we are used to in mathematics. But now the problem is, what happens if the function is not total? I mean, this one is total. If you apply it to any number, it will terminate and give you a proper result. But what about the following function? So if I have the following nice function, which is called non-term, for obvious reasons. Non-term also takes an integer and returns an integer. But as the name suggests, it doesn't terminate. So if I call non-term with the number x, non-term calls itself recursively with x plus 1. So non-term x plus 1. Now that's a perfectly legal Haskell program. I mean, we defined the syntax of Haskell, and the syntax allows us to write such programs. So they need semantics. They need to have a meaning. So we have to map the Haskell expression non-term to some mathematical object, and the question is, to which? Should we also map it to the function that takes a number and squares it? Well, obviously no, because this is not the semantics of it. I mean, if you write this and then you call non-term with 5 and you get 25 as a result, then you are surprised. Because this is not what we expected from Haskell. This is not the semantics that we want to define. Instead, we want a semantics where if we call non-term with 5, it doesn't terminate. So what do we do? Well, the solution is we will not only regard numbers, but we also have to regard values that stand for undefinedness. So we introduce a special mathematical object or mathematical value which stands for undefinedness, and this is written like this. So it's a capital T turned around, and this is pronounced bottom. So this is called bottom, and this stands for undefinedness, which stands for undefined. And then it's clear what the semantics of non-term is. So then non-term, this Haskell expression, is mapped to the function that takes a number and maps it to bottom. So if I apply it to 5, I get bottom. If I apply it to 7, I get bottom as well. And if I apply it to bottom, I get bottom as well. So this returns bottom all the time because this is always undefined for every argument. To a function that always returns bottom. And so this is a mathematical object. It's a function. Well, it doesn't operate only on numbers. It also operates on this special value bottom, which stands for undefined. And, well, now we can define a clear mapping like this. So this makes sense. And maybe I should stress that this mapping from Haskell expressions to mathematical objects, we only define this for well-typed Haskell expressions. I mean, if the expression is not well-typed, so something like non-term true, I mean, that's not a legal Haskell expression, and so we don't have to define any semantics for it because these expressions cannot occur in Haskell programs. They will be rejected anyway by type checking. So we only define the semantics for well-typed Haskell expressions and programs. So non-well-typed Haskell expressions or programs, they have no semantics. We don't have to consider them. And programs. And how to check whether an expression or a program is well-typed, how to do this automatically, we will come to that later in chapter 4. And to make life simple, let's first only look at Haskell expressions and types that are monomorphically typed, so where we have no polymorphism, no type variables. We will extend this later on to full polymorphic types, but to make life easy, we start with expressions that have a type where no type variables occur. So first, only regard expressions and programs with monomorphic types. And monomorphic is the contrary of polymorphic. With monomorphic types. So monomorphic means not polymorphic. Type. So no type variables. Let's exclude type variables for the moment, and we will introduce them afterwards. So let's regard one type after the other, and let's see for each Haskell type what are the mathematical objects that we will map Haskell expressions of this type to. So let's try to solve the following problem. So for each monomorphic Haskell type, we will now define a set of mathematical objects that represent the values that we can map expressions of this type to. So for each monomorphic Haskell type T, define a set of mathematical objects such that every Haskell expression of type T is mapped to an object of the set. So let's do this for the different types. And, well, let's start with the primitive types, with the simple types. So let's start with the type int. So objects of type int, things like 2 plus 1, for example. To what mathematical objects will we map these expressions? Well, to numbers, to integer numbers. So int expressions are mapped to values from the integer numbers. And, well, what are the integer numbers? 0, 1, minus 1, and so on. But is this sufficient? Well, no, it's not sufficient, because we had already one Haskell expression where this would not be sufficient. If you look at this non-term function up there, I mean, non-term 5. Non-term 5 is an expression of type int. So non-term 5 has to be mapped to some mathematical value. And we should not map it to 0 and not to 1 and not to minus 1, but to bottom. So the set of objects that we need here is not just the integer numbers, but in addition we need an extra value for undefinedness. And now, indeed, we can map every integer expression to a sensible mathematical object. Of course, we have to discuss how to define this mapping, but that will come later. At the moment, we will just think about how do the sets of mathematical objects look like that we need for the different Haskell types. And OK, this is not Z anymore, but it's Z plus this extra bottom value, and we call this set Z bottom. So Z index bottom. And this bottom value is the undefined value for this set, for this integer set. So this should be distinguished from the undefined value for Booleans and the undefined value for floats. So they have different undefined values. So this is the undefined value bottom of the set Z bottom. Now, this looks ugly, but so this should distinguish this. Let's look at Booleans, so to make this completely clear. So Boole expressions are mapped to values from the following set. Well, if this is true and false, then obviously this is not sufficient, because we can also think of Boolean expressions that are undefined. I mean, you can write non-terminating functions that return something Boolean. So we also need a third value here for undefinedness. And to distinguish this bottom from this bottom, we give it an index as well. So this set now is B bottom, and this should be indexed by V bottom. OK, now you can guess what happens with float expressions or character expressions. I mean, that works in a similar way. And now if we look at these sets, so this set Z bottom or the set B bottom, then we see that the elements in this set, yes?
Not infinite, but it's bounded. So if you want to have infinite, all numbers of that, you should use integer.
Yeah, well, this might contain too much. So if you only have 32-bit integers, then you wouldn't need all of these values, but for sure all of the needed values are in there. So for int, this is okay. For integer, it would also be okay. There you really need all integers. So this might contain too much, but for sure it contains enough. Okay, now if we look at these sets here, we can see that some elements are more defined than others. So more precisely here, it's pretty clear because this is completely undefined, and 0 is defined, completely defined, 1 is completely defined, -1 is completely defined. So it often makes sense to order the elements in these sets by their definedness. Let's do this. So we call these things, so these sets like Z bottom, B bottom, and so on, they are called domains because, well, we use them as the values for Haskell expressions are called domains. And one typically is interested in ordering the elements in such a domain by their definedness. One often orders the elements in a domain D by their definedness. And so for every domain D, we introduce an order which is written like this. So this is it looks a bit like the subset relation, but this is written in square. So, I mean, subset relation looks like this. And here we have the same thing, but with squares to distinguish it from the subset relation. So this is a relation between elements in a domain. And we say that X stands in this relation with Y. So if X and Y are elements of the domain D, then this means that X is less defined or equal than Y. So this is more defined than that. So this means X is less defined or equal to Y. So let's look at our examples. What about Z bottom? How is Z bottom ordered? So in Z bottom, we have this bottom thing. And clearly, this is less defined or equal than 0, because this is not defined and this is defined. And clearly, this is also less defined or equal to 1, and so on. Now, what about this? Is this also true? Is 0 less defined or equal to 1? Well, is 0 less defined than 1? No. 0 is defined, 1 is defined as well. And second question is 0 equal to 1? No, they are not equal. So this does not hold. 0 and 1, so this is a comparison by definedness. This is not a comparison by how large this number is. I mean, 0 and 1 and -1, all these numbers are equally defined. They are completely defined, and they are not equal. So 0 is not less defined or equal than 1. And similarly, 1 is, of course, also not less defined or equal to 0. So if you want to depict this order graphically, then it looks like this. So it looks like this. The meaning of this picture should be the following. So these arcs should indicate less defined. So bottom is less defined than 0. Bottom is less defined than 1. Bottom is less defined than 2, and so on. And these things are incomparable. So 0, 1, 2, 3, -1, they are all completely defined. So in other words, they're just two stages of definedness. Either things are completely undefined, then they are here, or they are completely defined, then they are there. And domains that look like this, where you have either complete definedness or complete undefinedness, these domains are called flat And so Z bottom is a flat domain. And of course, the same thing is true for B bottom, which is the domain for the Boolean expressions, and also for C bottom, which is the domain for characters. I mean, these are just all the characters plus bottom. And also F bottom, which is the domain for floating point numbers. These are just all floating point numbers plus bottom. So all of these base domains, these domains for the primitive built-in data structures, they are all flat. Things are either defined or undefined. But this is only the case for these very simple domains. For the more interesting domains, we will see that we have different stages of definedness. And before I show this, I have to wipe the board. OK, so we see that Z bottom, B bottom, C bottom for the characters, and F bottom for the floating points. They are all flat domains. And that means values are either bottom, so completely undefined, or completely defined. Are either completely undefined or completely defined. And to save some energy with writing, if the domain D is clear from the context, then we omit this index D. So if D is clear from the context, then we write just bottom instead of bottom D. And we also write less defined or equal without index instead of less defined or equal with index D. So this eases the notation a bit. And, well, we can think about what properties does this less defined or equal relation have. So you've probably heard of several properties that relations might have. And so what are the properties of this less defined or equal relation? So the properties of this less defined or equal relation, well, it has three main properties. The first property is reflexivity. What does that mean? Well, it means that every element stands in relation to itself. So for all values of the domain, we have that x is less defined or equal to x. Yeah, that obviously holds because, well, x is equal to x. And it's also, well, x and x are both defined as both are equally undefined or equally defined. I mean, they are just equal. So that clearly holds. Another property that holds is transitivity. So what does that mean? That means that if I have three objects, x, y, and z, and I know that x is less defined or equal to y, and I know that y is less defined or equal to z, then I can infer that x is less defined or equal to z. So this implies that x is less defined or equal to z. Well, yeah, why is that true? Well, if one of these, if we have equality for one of these two relations, then it's clear. And otherwise, x is really less defined than y, and y is less defined than z, then yeah, x must be less defined than z as well. So that looks plausible. And, well, what about symmetry? So if I have x and y, and x is less defined or equal to y, and y is less defined or equal to x. Can this happen? That you have two values, one is less defined or equal to the other, and vice versa. Mm-hmm.
Yes, that can happen, but then x has to be equal to y.
Right. So if this happens, then this implies that x and y are equal. And this property is not called symmetry, because symmetry means that whenever x stands in relation with y, then y stands in relation with x. But this is called anti-symmetry. So this is anti-symmetry. And a relation that satisfies these two properties, transitivity and anti-symmetry, is called an order. So every transitive and antisymmetric relation is called an order. It's called an order, Ordnung in German. It's called an order. The German word is Ordnung. And so this is an order, and it's also reflexive, so it's a reflexive order. So this is a reflexive order. So just to remind you that this is nothing new. Do you know other reflexive orders from your everyday life? Well, everyday life means you attend mathematics lectures, or you did maths in high school. So what reflexive orders do you know from high school, I hope? Set inclusion. So set inclusion is also a reflexive order. Do you know more? If you think of numbers, greater equal or less than equal, these are, so less than equal or greater equal, they are also reflexive orders. So this is something rather common, and you dealt with this already in school, I hope. And well, this is another reflexive order that you didn't deal with in school, most likely. But it's just the same thing as, well, it's just something that is reflexive, transitive, and antisymmetric. And okay, now that we introduced these notions, let's also define this relation formally for these base domains. So for Z bottom, B bottom, C bottom, and F bottom. So let's formally define this relation for the base domains. So this is definition 211, and it defines this relation on the base domains. So let D be a base domain, and the base domains are the integers with bottom, the booleans with bottom, the characters with bottom, or the floating point numbers with bottom. And then how is this relation defined? Then we define the following for all objects D and D prime from this domain. We say that D is less defined or equal to D prime if and only if, and to save some chalk, instead of writing if and only if, one often writes if with two F's, and this is a shorthand for if and only if. So if I have if with just one F, it means if, and if I have if with two F's, it means if and only if. So this implies the thing that is just coming now, and vice versa. So this holds if, well, there are two possibilities. One possibility is that D is bottom, or the other possibility is that D and D prime are equal. So this is the only possibility to have that D is less defined or equal to D prime. Either they are equal or D is bottom. D prime can be bottom, but can also be anything else. Okay, and such domains are called flat. We mentioned this already. And now we can think about whether there are other domains. And we should stress that this order is, of course, a partial order. So this is usually not total, because indeed we have that in Z bottom 0 is not less defined or equal than 1, and 1 is also not less defined or equal than 0. And such orders which are potentially not total are called partial. Yeah, one moment. So it's a partial order, a partial reflexive order. Yes?
Why don't we say 0 is equally defined to 1?
Well, it's okay. We could define it differently. I mean, many possible definitions are possible. You can define whatever you like. But in the end, we will use this definition of less defined or equal to determine the semantics. And this will become crucial as soon as we have recursively defined functions. And then we will build something like a chain of approximations to the semantics, and things will get more and more defined. And then you will see that this is the right definition, because if you would say, well, 0, if you have one iteration where your function computes 0, and the next iteration it computes 5, and the next it computes -5, and you have the impression this gets more and more defined, then you get complete nonsense as a limit of your approximation. Whereas what we want is that as the limit of the approximation, we get the desired semantics. So if we define it like that, we get the right thing. If we define it differently, we get the wrong thing. And maybe you should ask this question again when we really come to the definition of Haskell's semantics. So I mean, at the moment, we just define these domains and how to compare the objects in there. And so it's indeed important to keep in mind that this means less defined or equal, and not less defined or equally defined. Less defined or equal. And 0 and 1, 0 is not less defined than 1, and they are not equal, and so they don't stand in relation. I agree that they are equally defined, but that's not what this relation looks for. Okay, so up to now we had just these flat domains. So things are either completely defined or not defined at all. But this is only true for these very simple domains, and as soon as we have a bit more interesting domains or a bit more interesting types, this is not true anymore. So what happens if we have Haskell types that are not as simple as int, bool, character, and float? Well, and the next more challenging step is maybe to look at tuples. So in Haskell, you may have tuples, for example, pairs of integers. And if you have pairs of integers, then suddenly we have different stages of definedness. So the next step is how do the domains for tuple types look like? How could this look like? And well, here it makes so e.g. let's look at int. So this is a legal Haskell type, and the question is to what objects should we map expressions of the type int. So, well, what happens if we have, well, no, if we have 2 plus 3 and 5 plus 3. So that's a legal Haskell expression, and that, of course, is mapped to, well, 2 plus 3 should be 5, 5, 8. So this Haskell expression should be mapped to this value. So the domain for this type should contain pairs of numbers. Okay, but it can get more complicated. We might also have non-term 0 and 5 plus 3. And to what should we map this? So this we should map to also to a pair. Well, this should be mapped to something where the second component is 8. And this should be mapped to something where the first component is bottom. And well, if we turn this around, so 2 plus 3 and non-term 0, what will this be mapped to? Well, obviously to 5 bottom Okay, we could also have non-term 0 in both components. And this should obviously be mapped to bottom, bottom. So we see already that there are lots of values that we need in this domain for int, int. And well, if we now compare these things for definedness, we see that it's a bit more tricky than before, because now we can have different stages of definedness. So let's try to compare them. So what is less defined than what? So bottom, bottom. Is this less defined than this? Yes, because, well, in the first component we have bottom here and we have 5 here. And so if we go from here to here, we clearly make the first component more defined. And the second component remains as undefined as before. So this should be less defined than or equal to 5 bottom. And then this should be less defined or equal than that, because now if we go from 5 to 5, this remains the same. But here we go from bottom to 8, so this becomes more defined. So that looks good. And of course, the same is also true if we compare bottom, bottom with bottom 8. And, well, bottom 8 is clearly less defined or equal than 5, 8. And what about if we compare these two things? So 5 bottom and bottom 8. Is this less defined or equal to this? No. I mean, in the first component, things even get, well, this is not more defined, this is even less defined than 5. For the second component, we make it more defined, but yeah, this we cannot compare. So this cannot be compared, and of course, the converse doesn't hold either. So, so we now see that suddenly these chains of elements that become more and more defined can be longer than just 2. I mean, now this is pretty much completely undefined. This is a bit more defined, but not completely defined. And this is completely defined. So now we have, we can go 3 steps. And clearly, if we have tuples not with 2 components, but with 3 components, then it's not difficult to imagine a sequence where you have 4 steps in increasing definedness. Yes?
Should bottom itself be in the domain?
That's a very good question. That's indeed a very good question. Yes, the answer is yes. And since you asked this question, let's look at an example which illustrates this. Because the problem indeed is, if we look at the following. So there should also be another bottom. So there is another bottom which is even below this bottom-bottom pair over here. And to illustrate this, we need, well, let's look at an example. So suppose I have something of type int int, some value c of type int int, and c is just mapped to itself. And this thing is less defined than this here, because this c behaves different from something like this in Haskell. And why this is the case, I will show you later. But indeed, we need another bottom value which is even below this here. So this c over here, this would be mapped to bottom. So in fact, we have even sequences of this form. So this is completely undefined. Here we don't even have the structure that this is a tuple with 2 components, both of which are bottom. And so indeed, we have already here, we have sequences of length 4 if we look at this. So indeed, we need this. Yes?
If we wouldn't know yet that as a tuple, it would be the correct type.
True. Okay, so let me illustrate why this is needed. So suppose I have 2 functions. F goes from int int to int, and it does pattern matching like this. F of xy is 0, but g goes also from int to int, and g of z is 0. So the only difference is that here I write z and there I write the tuple. And now what happens if I call f and g? So what happens if I call fc? What happens if I call f with non-term 0? I just write nt0 because non-term is such a long thing. What happens if I call gc, and what happens if I call g with non-term 0, non-term 0? I mean, the question is, does this thing behave differently from this? So is something that is completely undefined of type int, is that different from a tuple where both components are completely undefined? And in Haskell, the answer is yes, this is different, because f and g, if you apply a function to, well, one time you apply it to c and one time you apply it to this, you see the difference in behavior, because fc will not terminate. So this is not terminating, whereas this is terminating. And, well, here both are terminating. So this tuple is like a constructor. So even though you are right, I know that this is something of type int, this plays the role of a data constructor. So this is the data constructor for tuples of length 2. And so this thing will be, if I call fc, I will try to evaluate c until I know that it is a tuple, that it starts with this tuple constructor. Although you're right, it's clear from the type. But this is how Haskell operates. And so Haskell, if I do this, it will start evaluating c until I have a tuple with two components. And it will never reach this stage because c doesn't terminate. So this thing will not terminate, and this thing does terminate. And so this means that c and non-term 0 should not be mapped to the same object, because they do not describe the same object. So this is more defined than this. So this is confusing and surprising. And indeed, when I gave the lecture the first time, I made this mistake as well. And but then later on, we found out that this is wrong. So this is there's really a difference. So your comment was right. For the domain for int, indeed, I need this thing as well. OK, but so the domain will be. So the domain will be, well, it's z bottom cross z bottom plus an additional bottom element. So plus an additional bottom element. And how to denote this, we will see later on. But indeed, this will be needed. But, well, we introduced this formally later on. Now, at the moment, let's first define how this less defined or equal relation operates on tuples. And we've seen how this works. Tuples are compared component-wise. So we say that one tuple is less defined than another if this less defined or equal to another if this holds for each component. So if we do this component-wise, we get the following definition. So let's extend this order now on product domains. So this is definition 212, and we now define this relation on product domains. So suppose that we already have some domains d1 to dn. B domains, and n is at least 2, so n is greater or equal to 2. Then we define the relation less defined or equal on the Cartesian product d1 cross dn. So this is a relation comparing n tuples. So we compare this as follows. So well, if D1 and Dn are domains, then D1 cross Dn is also called a domain. And the relation is defined as follows. Well, I have to compare n tuples. So the first component is from D1, capital D1, the second from capital D2, and the last one is from Dn. And the question is, when is this less defined or equal to the tuple D1 prime to Dn prime? And this holds, well, if the same is true for every component. So the first component, D1 must be less defined or equal than D1 prime. And here we take the less defined or equal order from domain number 1. And, well, the same has to be true for D2 and also for Dn. So Dn is less defined or equal than Dn prime. And if this is the definition, then it's clear what the smallest element is. So the smallest element of D1 cross Dn, smallest with respect to the less defined or equal relation, is the following one. It's the bottom element of D1, bottom element of D2, and bottom element of Dn. So this tuple is the smallest element of this cross product, and this is also sometimes denoted as the bottom element of D1 cross Dn. Sorry? No, because this set D1 cross Dn, this only contains tuples. This does not contain bottom on its own. So this thing is really just bottom, 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 0, 0, bottom, and so on. And as the domain for int, comma int, we will later on use this plus an additional bottom element. So this thing is z bottom cross z bottom plus an additional element, namely bottom. And if you want to know the index here, this is the index z bottom cross z bottom with an additional bottom element. Okay, looks ugly. And if you want to know the indices here, well, here it's just z bottom. Okay? So this will be the domain for int int. This will be the domain for int comma int. But currently I just defined less defined or equal on this thing. And we will then extend this to less defined or equal on this thing. It works the same, but this extra bottom element is smaller than anything else. Yes?
In the example, bottom 1 and is bottom 1 and 1, 2, those tuples, then bottom 1 should not be less defined or equal than 1, 2.
Bottom 1 and 1, 2, yes, they should not be comparable.
But apparently the first one is less defined.
No, less defined or equal. So this is then component-wise. So yes, this is less defined than this. But this is not less defined than this, and it's also not equal. So therefore, this does not hold. Right? So it's not less defined or equally defined. No, it's less defined or identical. So this means, maybe I should say less defined or identical. And well, if you compare 1 and 2, they are both fully defined and they are not identical. And therefore, well, 1 is not less defined or equal to 2, and therefore it doesn't hold for these components either. Okay, maybe writing equal here is confusing. Replace it by identical. That makes it clearer, maybe. Okay, so this is really something you have to keep in mind. 1 is not less defined or equal to 2. And 2 is not less defined or equal to 1. Okay, but after a while you get used to that, I hope. Okay, so we have seen that we've seen how to define less defined or equal on these products. And of course, you might ask, is this then still a reflexive partial order? And so that's something you can prove. And the answer is, of course, yes. So it's not difficult to prove that if you have this, d1 cross dn is a reflexive partial order. So that's the main statement of the lemma. So more precisely, the lemma says that if all these orders on the domains d1 to dn, so for all di, if they are all reflexive partial orders, then the same is true for the relation on the product of these domains. Then this is also a reflexive order. So this is something we can prove. And since we didn't yet prove anything in this lecture, let's do this, or at least let's start with it. It's very simple. Let's make sure we don't forget how the definition is for products. So it looks like this. If you depict this again graphically, then we have this situation. Now I didn't include this extra bottom because at the moment I have just z bottom cross z bottom, not with this extra bottom element. If I just have z bottom cross z bottom, I really have just pairs, and then they are ordered like this. So bottom bottom is less defined than 0 bottom, or bottom 0, or bottom 1, or 1 bottom, and so on. And if I replace the remaining bottom by some number, I get even more defined. So 0 bottom is less defined than 0, 0, or 0, 1, or 0, 2. And similarly, bottom 0 is less defined than 0, 0, or 1, 0, or 2, 0. And so we have now these different stages of definedness. And if we have no lines between two elements, then they are incomparable. So that means that this, and this, and this, and this, they are all incomparable. OK, let's try to prove this lemma, or at least let's start with proving this lemma. So what do we have to prove? We have to prove that this relation on the product of d1 to dn is reflexive, transitive, and antisymmetric. So let's start with reflexivity. OK, what do we have to show? We have to show that if we have a component, a tuple from d1 to dn, so something like this, that it stands in relation with itself. So we have to prove that this is less defined or equal to itself. And well, how is this relation defined? The relation is defined such that this holds if and only if d1 stands in relation with d1, d2 stands in relation with d2, and so on. So by definition, this is equivalent to d1 stands in relation to d1, and so on, and dn stands in relation with dn. Yeah, and why does this hold? Well, this holds because by assumption, all of these relations are reflexive. So if this is reflexive, then this must hold. So this holds by reflexivity of relation number 1 to relation number n. So this follows immediately. And well, the same is true for transitivity and antisymmetry. Should we do one more? No. Let's do one more. Let's do transitivity. But omit anti-symmetry, which works in the same way. So what do we have to show? Well, we have to show that if d1 to dn is less defined or equal to d1 prime to dn prime, or that's not right to show. Let's say let this hold, and moreover, this prime thing is less defined or equal to d1 double prime up to dn double prime. And what we want to show is that then this first tuple is also less defined or equal to this last tuple. Now, what do we know? Well, by definition, if we have this, then this means that the first component here is less defined or equal to the first component there, and moreover, it's also less defined or equal to the first component there. So by definition, we know that d1 is less defined or equal to d1 prime, and d1 prime is less defined or equal to d1 double prime. And this holds not only for the first component, but also for the second, the third, and the last component. So we also have that dn is less defined or equal than dn prime, and this in turn is less defined or equal to dn double prime. And now how can we proceed? We want to show transitivity. We know that these things are transitive, and we want to show that this thing is also transitive. So any idea, or is that too simple? Yes?
So we know that d1 is less than equal to d1 prime prime, and up to dl is less than equal to dn prime prime. So this is what we want to show as the whole relation is defined component-wise.
Right, exactly. So since we know that all these things are transitive, so since they are all transitive, we know this, and as you just pointed out, the definition of this thing is we compare component-wise. So if this all holds, then by the definition of this order on the Cartesian product, we know that d1 to dn is less defined or equal to d1 double prime and dn double prime. And right, that's indeed it. And anti-symmetry is proven in just the same way. So anti-symmetry works analogously. So this I will omit, and this ends the proof. Now we have seen that we can, if we have such a less defined or equal order on some domain, we can lift it to the Cartesian product. But of course, if you think of the Haskell types, well, we can create new types by building tuples. But another way to create new types is by using functions. So for example, the type int arrow int, that's the type of functions from int to int. And so we will also need a domain for functions. And then we want to compare these functions also by their definedness. So the next step is, how do we extend this concept of comparing objects by definedness? How do we extend this to functions? So to have a domain also for function types, so something like int to int, like int to int, we extend this less defined or equal relation not only to tuples, but also to functions. Also to functions. So let's do this. And well, how would we do this? So let's just define this. And now we want to have this on functions. Well, and the idea is rather similar to this tuple, to the extension for tuples. But if you have tuples, we compare them component-wise for their definedness. If we have functions, we compare them result-wise. So for every, if we have two functions f and g, then we apply them to all possible arguments, and the result of the one function has to be less defined or equal than the result of the other function. And we have to do this for every argument. And if this is the case, then we say that the first function f is less defined or equal to g. So if we have two functions f and g, let these be functions from a domain D1 to a domain D2. To a domain D2. And then we define that f is less defined or equal with respect to this set of functions from D1 to D2. So f is less defined or equal to g if and only if, well, if this holds component-wise or argument-wise. So no matter to which argument we apply these functions, so we have fd and gd, then the result of f must be less defined or equal than the result of g. So this must be less defined or equal to gd. And of course, f of d, so d must be from d1 for all d from d1. And fd then is from d2. And gd is also from d2. So here we need the less defined or equal relation on the values from d2. And so what is the smallest function in this sense? So what is the function that is less defined or equal to any other function? So the smallest function, which we denote by bottom and index d1 to d2, is the function that well, what does this function do? So for every argument, it must do something that is less defined or equal than anything else. So it has to return bottom for every argument. So it's the function that maps any object from D1 to the completely undefined value of D2. So in that sense, this is the completely undefined function. It maps everything to undefined. This is the smallest function, and afterwards it can only get better. It can only get more and more defined. And, well, we will see several examples of these kinds of functions. Now we defined this on functions as well, and of course the natural question is again, is this still, yes? Well, it depends. There are many functions that are not always non-terminating. So there are some functions that are terminating on certain arguments and non-terminating on others. So the function that is always non-terminating for every possible argument, that's the smallest one. But a function that is terminating, let's say if we look at numbers, that is terminating for positive numbers but non-terminating for negative numbers is a bit more, is a bit greater. And a function that is terminating everywhere is even more greater. Yes?
Doesn't this imply that D2 has a single unique bottom element? So if I have a function that returns a function where I can't think of a single bottom element, what is the bottom element of D2 there?
Well, every domain has one unique smallest bottom element, indeed. So every domain D has a unique smallest element which we denote by bottom index D. And so for the integers, it's bottom, z bottom, and so on. If we have tuples, it's the tuple with all these bottoms, and if we have functions, it's this function. So, I mean, D2 must already be a domain, and then it has this unique bottom element. And then D1 arrow D2 also has a unique bottom element, namely this function here that maps every element to this thing. And if we have a function, if we have a higher order function whose result is again a function, then this makes also sense. Because then the result would be the smallest function from D2, where D2 in fact might also contain functions. Okay. If we later on define the domains formally, it will turn out that we will not take all functions here, but just a subset of the functions. And we will see this in the next subsection, because, I mean, this contains all functions, including the non-computable functions, and we don't need these non-computable functions, because in Haskell we cannot write programs for every possible functions. I mean, in particular, for non-computable functions, there's no chance to write a Haskell program for them. So we will reduce this a bit. But, well, that will come afterwards. At the moment, let's look at all the functions, and then still this less defined or equal can be defined on the set of all functions. So that still makes sense. And now we can ask again, is this a reflexive partial order? So is this relation on functions, is this also reflexive, transitive, and antisymmetric? And the answer is yes, and that's, again, easy to prove, more or less as difficult as for product domains. So we can formulate a similar lemma as for products. So this is lemma 215, and this lemma simply states that on functions, this is a reflexive order, and this holds provided that on D2 this is also a reflexive order. So the lemma states if this is a reflexive order on D2, then the less defined or equal relation on this set of functions is also a reflexive order. And, well, the proof is almost identical or very similar to the one of the lemma that we just had. So to lemma 213. Similar to lemma 213, so I won't do this here again, but indeed it's not difficult. Okay, so this introduces the basic ideas for these values that we will look at and how to compare these values by their definedness. And now, as I just mentioned, we will restrict the set of functions that we will look at for the semantics. So not all of these functions will really be used, but we will only take functions that satisfy certain properties, namely the properties of monotonicity and of continuity. And therefore, this is the next subsection. We will now restrict the functions that we will need for the semantics. And we restrict them to monotonicity and continuity. So monotonic and continuous functions. The German translation of continuous is stetig. So I hope you have heard this before in your mathematics lectures. Okay, so the idea is we want to restrict the set of functions from D1 to D2 that are used for the semantics of Haskell. So we don't need them all. And so to do this, let's introduce some properties of functions, and well, monotonicity and continuity will be properties of functions, but before we introduce them, let's introduce a simpler property, namely the property of strictness. Because essentially what we do is we look at when we want to define the semantics, we look at the definition of the Haskell function, and well, the definition typically tells us what the function does on defined values, but we always have to extend the function so that it also can work on undefined values, because every function you can apply to arguments that are undefined. And then when we're defining the semantics, we have to explain what happens if you apply your function to an undefined value. And this leads to the following definition. Let's first define it and then illustrate it by some examples. So what does it mean if a function is strict? So strictness of functions. So suppose we have a function going from one set A to another set B. So let f be a function which goes from A to B. And the question is, how can we, so for example, A could be the integers and B could also be the integers. And then the question is, how could we extend this function so that it also operates on bottom? Because if we want to define the semantics, then we also have to say what happens if the function is applied to something that is undefined. So let A index bottom be the set A plus a fresh element bottom from A bottom. And then every function that is like f, but also is extended to work on this bottom element, is called an extension of f. So every function f prime, which goes from A bottom to B, and which operates like f on all elements of A. So f of D is the same as f prime of D for all D from A. Every such function is called an extension of f. So it simply means that we extend f to work also on bottom. And now the question is, how are these functions extended? And well, one possibility is to say whenever the argument is bottom, then the result is bottom as well. And if we do this, then we say the function is strict. So as soon as some argument is undefined, the function also says undefined. So this is the definition of strictness, and that's what I will define now. So if we have a function which may have several arguments, so it may go from d1 cross dn to some d, such a function is called strict if the following holds. The function returns bottom as soon as one of its arguments is bottom. So this returns bottom d. If this holds whenever some di is the bottom element of di. So it's sufficient to have one argument undefined, and then g immediately returns bottom. If this is the case, then we say the function is strict. And now the question is, how do we do this in Haskell? I mean, in Haskell, whenever we have a function of type int to int, we have to say in the semantics what happens if we apply it to bottom. And should we always choose this strict extension? So as soon as we apply it to bottom, we get undefinedness, or should we do something else? And yeah, how to do this and how to select the right semantics, we will continue this on Monday. So see you again on Monday.